Hello and welcome. Mr. Johnson here, and in this video we're going to be looking at the four quantum numbers N, L, M sub L, and M sub S. So let's go on and get right into it. So the first question becomes, what in the world are the four quantum numbers? Well, this is a set of numbers that when you write them out consecutively, they're going to tell you about the properties of atomic orbitals as well as the electrons that are in that orbital. And I'll get to what an atomic orbital is in just a little bit. The easiest way to think about the four quantum numbers is to think about them as like a mailing address. Okay? What the four quantum numbers do is they allow us to narrow in on a single specific electron that we're wanting to study. And just like a mailing address, if you're going to mail a letter, you only really need four things. You need the state, the city, the street name, and the house number. And that's the way these four quantum numbers work. Between N, L, M sub L, and M sub S, it's like those four things that you need to be able to mail a letter. These allow us to narrow on down to a specific electron that we're wanting to study. So the first of those is what we call the principal quantum number. This is symbolized by N. And the principal quantum number has values of 1 through 7 that tell us about the energy level where that electron is going to be, or we also refer to it as the energy shell. Okay? And as we go from 1 to 7, 1 is the lowest energy, N equals 7 is the highest energy. And what we find is that as that value of N increases from 1 to 2 to 3 on up to 7, the distance of an electron from the nucleus also increases. And because that distance increases between the nucleus and where the electron is, the potential energy of that electron also increases. Another nice thing about the value of N is that we can use this to calculate the maximum number of electrons to a specific energy level or energy shell using the equation 2n squared. So let's go on and look at some examples of values of N and calculating that maximum number of electrons. So if I'm going to go on and start out with the value of N equals 1, then when I'm looking at N equals 1, knowing that the max number of electrons equals 2n squared, then I can write out the equation 2n squared, where I now have 2 times my value of N, which is 1, which is going to be squared. And 1 squared is 1, so this simplifies down to 2 times 1, or simply 2 electrons max within energy level 1. If I move on to energy level 2, I can do the same type of math. 2n squared. So 2 times my value of N, which is 2. I'm going to square that value of N. 2 squared is 4. So I've got 2 times 4, which is 8 electrons maximum to energy level 2. If I go on to energy level 3, again using 2n squared, that's going to give me 2 times 3 squared. 3 squared is 9, and 2 times 9 gives me 18 electrons maximum. And we can continue doing this for N equals 4, 5, and 6. And we're going to get the maximum number of electrons that are able to go into that specific energy level. So how does this relate to periodic table? Well, first off, when you look at the periodic table, notice, again, N has values of 1 through 7. And when you look at how many periods are on the periodic table, notice there's 1, 2, 3, 4, 5, 6, 7 periods on the periodic table. Understand that lanthanum extends out into the lanthanide series, and then actinide extends out into the actinide series. Okay? Those two rows at the bottom of the periodic table, they actually jut out from the periodic table, so that as we're looking at similarities and properties down a column or down a family, those properties line up. Okay, so the main thing that I want you to see in this again is if I have 7 values of n, each value of n corresponds to a period on the periodic table. So if I look at n equals 1 again, and it has 2 electrons max, notice that period 1 has 2 elements maximum. When I move on to energy level 2, we calculated that this had 8 electrons max. And notice, in period 2, there are 1, 2, 3, 4, 5, 6, 7, 8 elements maximum. When we move on to energy level 3, we calculated that there are 18 electrons maximum. If we look at period 3, 1, 2, 3, 4, 5, 6, 7, 8, we still need 10 more electrons. So take a look. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I'll explain in the video just a little bit later how I knew to drop down to element 21 and count on to element 30 to get the remaining 10 electrons for energy level 3. But right now, what I'm wanting you to see again is that there is a direct connection between quantum numbers and the periodic table and the way that this is set up. So that is the first quantum number, n. Our second quantum number, this is what's called the angular momentum quantum number. And this is symbolized by the letter L. And this value is going to have values of 0 through n minus 1 for each value of n. This value of L tells us how many sublevels there are within an energy level. So for example, when I'm looking at n equals 1, this has 1 sublevel. Therefore, n equals 1 will only have 1 value of L. When I look at energy level 2, n equals 2, I'm going to have 2 sublevels. So in other words, n equals 2 will have 2 values of L. If I move on to energy level 3, n equals 3, I'm going to have 3 sublevels and therefore 3 values of L. And what we do, instead of having to call off a bunch of numbers, we go on to designate these sublevels using letters. So anytime you see L equals 0, we refer to that as an S sublevel. If you see L equals 1, that's a P sublevel. L equals 2 is a D sublevel. L equals 3 is an F sublevel. And while we have letter designations for L equals 4, 5, and 6, you typically aren't going to see those in a textbook because they don't even show up on the periodic table. Okay? So let's take a look at how we get these values of L. So if I'm looking again, starting back at n equals 1, because n has a value of 1, I'm only going to have 1 value of L. And because L has integral values, or in other words, whole number values of 0 to n minus 1, that value of 0 is always going to be the first value. This n minus 1 will always be the final value of L. So when I look at n equals 1, because I've only got one L value, the first value being 0, n equals 1 only has 1 sublevel. And again, we'd call this an S sublevel. When I move to n equals 2, because n equals 2, I'm now going to have 2 values of L. And again, that first value is always 0. The final value is always going to be n minus 1. So in this case, n has a value of 2. So 2 minus 1 gives me 1. And that is my second value of L for n equals 2. Again, we would label these with letter designations. So we find that n equals 2 has an S sublevel and it has a P sublevel. When I move to n equals 3, again, because n equals 3, I'm going to have 3 values of L. And the first value is always 0. My final value is always n minus 1. So in this case, n equals 3. So 3 minus 1 is 2. And the whole number that comes between 0 and 2 is a value of 1. So what we find is energy level 3 has an S sublevel, a P sublevel, and a D sublevel. If I go on and look at n equals 4, because it equals 4, I'm going to have 4 values of L. The easiest way to do these numbers for L, instead of doing the first one is 0 and the final one is n minus 1, if you simply number them starting at 0, because L has integral values, if you simply number them, your final value is automatically going to come out as your n minus 1. So for energy level 4, we find it has an S, a P, a D, and an F sublevel. So how does this relate to the periodic table? So let's take a look again. So when I look at n equals 1, and that value of L, or only an S sublevel, in period 1, hydrogen and helium are part of what we refer to as the S block. Okay? Now the reason why I know I need 2 elements is if you remember, energy level 1 can hold a maximum of 2 electrons. So as a result, that S sublevel can hold a maximum of 2 electrons. And if we're relating our quantum numbers back to the periodic table, and energy level 1 and the S sublevel hold a max of 2 electrons, then it stands to reason that period 1, the S block, would have a maximum of just 2 elements. When I look now at n equals 2, I had an L equals 0 and an L equals 1, which means I had an S sublevel and a P sublevel. So if I look at period 2 on the periodic table, it's also going to have an S block. That would be lithium and beryllium. But it's also going to have a P sublevel. And if I look across the periodic table still on period 2, this is what we refer to as the P block. Now here's what's really nice. We said that energy level 2 maxes at 8 electrons. And notice there is a total of 2 plus another 6 elements to get our total of 8 elements that correspond to the maximum of 8 electrons. So when I look at n equals 3, L equals 0, L equals 1, L equals 2, which means I have an S sublevel, a P sublevel, and a D sublevel. That means on the periodic table, period 3 should also have an S sublevel. It should have a P sublevel represented, so my S block and my P block, and then also a D sublevel. So the only section that we haven't looked at yet is this center section. And that's how I knew earlier to drop down to element 21 through 30 to get the remaining 10 electrons that I needed to get energy level 3's maximum of 18 electrons. And if I count up the total number of electrons for period 3, I'm going to find 18 elements. So this is how I knew to drop down. What this also means is that when we go to look at energy level 4, n equals 4, L equals 0, L equals 1, L equals 2, and L equals 3. Energy level 4 is going to have an S, a P, a D, and an F sublevel, which means it needs to have an S, P, D, and an F block. So when I look at energy level 4, here's the S block for energy level 4, the P block for energy level 4, the D block for energy level 4, and now I need to account for the F sublevel on the periodic table. Well, that is down here. And I'm leaving off lanthanum because lanthanum actually belongs to the D block. So this is what we refer to down here as the F block. So this is the relationship again. Now, not just N has values of 1 through 7, so we have 7 periods, but each energy level has certain sublevels, and those sublevels are represented by the blocks of the periodic table. So that is the second quantum number. So now the third quantum number. This is what we refer to as the magnetic quantum number. And the magnetic quantum number is symbolized by M or M sub L. Okay? Or M sub L. Historically, it's just been M. More modern textbooks are going to say M sub L. Okay? So this is what's denoting an orbital. And an orbital is a region of space within a sublevel. So we've got an energy level. Within that energy level, there is a sublevel. And then within that sublevel, there are regions of space. And those regions of space lie along the X, Y, and Z axis of three-dimensional space, or some combination of the X, Y, and Z. As far as the values for M sub L, this is going to have integral or whole number values of negative L to positive L, including the value of 0. And as I just said, orbitals, they lie within specific regions of the X, Y, and Z dimensions, and therefore they give rise to specific sublevel shapes. For example, the S sublevel has a spherical shape. A P sublevel we refer to as having a dumbbell shape, and on it goes. The other key thing about orbitals is they hold a maximum of 2 electrons per orbital. Right? So let's look at how we go about doing the M sub L values. So I'm going to start back at N equals 1. N equals 1, again, only has one L value, which is 0. And as far as the M sub L value, again, this is going to run negative L to positive L. By the way, you can also see it in textbooks as positive L to negative L, but I do it negative to positive because I like to think about this in terms of a number line. So if my value of L is 0, then I'm going to run from negative 0 to positive 0, or simply 0. This means that within energy level 1, that S sublevel, there is only one region of space for the electrons to go into. Right? And if you recall, energy level 1 has a maximum of 2 electrons. That means both of those electrons have to be in the S sublevel. And within the S sublevel, they both have to be within that one orbital. And this is where we get the idea that each orbital can only hold a maximum of 2 electrons. So when I look at N equals 2, I have 2 L values. Again, the first one is 0. The second one is equal to N minus 1. It's my final L value. So again, I have an S sublevel and a P sublevel. For the S sublevel, M sub L, again, equals 0. For L equals 1, M sub L now is going to run from negative L to positive L, or in other words, negative 1 all the way to positive 1. So I have 3 values for M sub L when I'm talking about a P sublevel. This is why it's important. Again, energy level 2 can hold 8 electrons max. Well, there is an idea called Aufbau. Refers to building up. And what Aufbau is typically used to notate is that within electron configurations, we're always going to take what came before and we're going to repeat that and then add on to it. So as a result, if in energy level 1, 2 electrons went into the s sublevel and those 2 electrons then into the single orbital, then it stands to reason in energy level 2, out of those 8 electrons, 2 of them are going to go into the s and therefore into that single orbital. That leaves 6 electrons remaining for the p sublevel. And if each orbital can hold 2 electrons, that accounts for those remaining 6. This is also why within the p block on the periodic table, we find 6 elements, because each element corresponds to an electron. If the p sublevel can hold 6 electrons, then the p block on the periodic table can hold 6 elements. Likewise, when we go on to n equals 3, I have 3 L values. The first one again is 0, and then we can simply number. So energy level 3 has an S, a P, and a D block, or a D sublevel. So for L equals 0, M sub L again equals 0, just like we saw for n equals 1 and for n equals 2. L equals 1 will have M sub L of -1, 0, and 1, just like we saw for energy level 2. And now my D sublevel, or L equals 2, it again will have M sub L values of -L through +L. So thinking back to the number line, that would be from -2 to +2. So -2, -1, 0, 1, and 2. And we can continue this idea of Aufbau. We look at energy level 3. If we follow the pattern, 2 of the 18 will be in the s sublevel and therefore in the single orbital. 6 of them will be in the p sublevel, divided equally amongst its 3 orbitals. So 2 electrons, 2 electrons, 2 electrons. And that leaves 10 electrons to the d sublevel. And if you remember on the periodic table, the d block, we had 10 elements. And again, these would be split evenly, with 2 of those 10 going into each of the 5 orbitals. So I'd have 2, 4, 6, 8, 10. So before I get to the last quantum number, I want to go back to this idea of the mailing address and how these quantum numbers narrow us down. Okay, so let's think about a theoretical element that has 280 electrons. That would be the maximum number of electrons to an atom if all 7 energy levels were completely filled. So I've got this theoretical element 280 with 280 electrons. That's a lot of electrons. And what we can do is say, all right, I want to find an electron and study it that's in energy level 3. Well, automatically, out of 280 electrons, we're now looking at just the 18 electrons that are in energy level 3. Then I can narrow it down even further and say, well, 280, energy level 3, down to 18. I want to look at an electron that's in the D sublevel. Now I'm down to these 10 electrons. Then I can say, within that D sublevel, I want it to be an orbital M sub L equals 0. Now I'm looking at those 2 electrons. So simply with the first 3 quantum numbers, out of 280 electrons, we can say, I want to look at them in n equals 3. We're down to 18. Within the D sublevel, we're down to 10. Within the orbital M sub L equals 0, I'm down to 2 electrons. So the fourth quantum number is going to tell me which of those two electrons I'm wanting to look at. So when we go to the periodic table, so you can see how this works out, again, if I'm looking at these first two columns, and you'll want to label your periodic table the same way, which if you would like a copy of this periodic table, okay, this ends up, oops, excuse me, I put up the wrong thing. There we are. Okay. You can go to this website, www.periodni.com. I will post this link in either the comments or the description for you. And you can download this periodic table. But this website, www.periodni.com, has lots of great resources and images that you can download and look at. That wonderful website. So thank you to them. They are not sponsoring this in any way, shape, form, or fashion, but I want to give credit where credit is due. So if you like this periodic table, and it's one of the best ones that I've found out there, that's where you can go and get it. Okay? So anyway, back to this. What you'll want to do is label your periodic table where these first two columns are what we refer to as, again, the S block. Then what I'm outlining in red, this is going to be the P block. What I'm outlining in green is our D block. And notice that I jut this in, right, around that LA to LU and then the AC to LR. And then the last thing that I'm going to block in blue, this is going to be the F block. Okay. Furthermore, what you're also most likely going to want to end up doing is numbering some things. Okay. And also should mention that on a lot of periodic tables, you'll find helium shifted directly over next to hydrogen so that they're in that S block together. Okay. The other thing that you're going to want to do, just as a recall, is scandium through zinc are actually part of energy level 3 or period 3. Yttrium through cadmium is part of 4. Hafnium through mercury is 5. And rutherfordium through Copernicum is 6. Over in the P block, boron through neon is still period 2. Aluminum through argon is period 3. Gallium through krypton is back to period 4. Then we've got period 5, 6, and 7. Within the F block, cerium through lutetium, that belongs actually to period 4. And thorium through lawrencium belongs to period 5. Lanthanum is actually 5D, and actinium is 6D. Okay, so you'll want to label your periodic table as such so that in a future video, whenever I do electron configurations, you've already got a periodic table that's set up exactly like it needs to be able to make sense of everything. So as far as how those quantum numbers, again, work on this, my values of N are given by the period. My S, P, and D blocks are representative of the S, P, D, and F sublevels. And then the number of elements in each block refer to the total number of electrons within a sublevel. Okay? So again, if I'm looking at energy level 2, the S block, 2 electrons, because energy level 2 S sublevel can only hold 2 electrons. If I'm looking at energy level 2, the P sublevel, total of 6 electrons. So period 2, the P block, a total of 6 elements. And again, we can go on and do the exact same thing when we're talking about the D block, and the F block. So I'm hoping that you're seeing that relationship between the quantum numbers and the periodic table. The reason why I've taken the time to do periodic table here is because the value of S, or M sub S, is not denoted on the periodic table at all. So let's look at that final quantum number. That final quantum number is what we refer to as the spin quantum number. And this is symbolized by S traditionally, or nowadays you'll see it as M sub S. As far as values, because each orbital can only hold 2 electrons, as we talked about, the 280 down to 18, down to 10, down to 2, we only have 2 values of S. And those 2 electrons, so that we can tell them apart, we tell them apart with their spin. So we're either going to use a positive 1/2, or what's called an up spin, or a negative 1/2 to denote what we refer to as the down spin. You can also hear the up spin referred to as a clockwise spin, the negative 1/2 as a counterclockwise spin. So going back to kind of the example and looking now at all 4 quantum numbers, my element of 280 electrons, I want to look at a specific electron in energy level 3. I'm down to 18. In the D sublevel, I'm looking at 10. In orbital M sub L equals 0. Now I've got 2 electrons. One of those spinning clockwise, one spinning counterclockwise. So positive 1/2 or negative 1/2. And as soon as I give that 4th and final quantum number, I'm looking at a single specific electron within that atom. So hopefully all of this has made sense to you. Hey, if not, please feel free to leave questions in the comments. If you've got ideas for a future video, leave those in the comments as well. Appreciate it. Thanks, and take care.